Okay, I think we can get started. I'll just add more people in the waiting room during the class. So this class, we're gonna finish up the NOx control and talk a little bit about the carbon dioxide control, okay? So let's still do a quick recap because we have finished up most of the NOx control contents, okay? So we mentioned that to control the NOx formation, nitrogen oxide formation, there are several ways to do this. So we have the in-combustion method. And we're mainly trying to deal with the NOx formation during the combustion when the fossil fuel is still in the boiler, right? And boiler or car engines. I will mention that for that NOx, we have either the fuel NOx or the thermal NOx. But for both of them, we can basically identify three parameters where we can control to reduce the NOx formation. So one is temperature, the other is the residence time, and third is oxygen. So if we can reduce all of these, then we can reduce the NOx formation, right? So that's why we can design different combustion techniques to reduce these parameters. So here, basically, I'm repeating myself. So we can reduce the peak temperature, reduce the gas residence time, and also reduce the oxygen content in the flame. So that's why we came up or narrowed down to these techniques, right? So the one that we talk quite a lot about is the overfire air, the OFA here, or the OSC. So basically, the way it works is we're going to burn the fuel under a fuel-rich condition. So we defined a parameter that's called the equivalence ratio. So basically, the equivalence ratio is larger than 1 in the fuel-rich flame, right? So basically, when we introduce the coparticles, if it's under the fuel-rich oxygen, there are basically less oxygen, then we're going to form some hydrocarbons that will further go up. And then when we introduce a stream of air that's over the fire, that's why it's called overfire air, right? Over the fire, and then the carbon and oxygen are going to react here. So basically, we're consuming the rest of the fossil fuel in there. So in this way, what we're achieving is, first, we're reducing the temperature, right? Because we introduced less oxygen into the flame, more fuel, the temperature would reduce. And also the oxygen amount is reduced, right? And since the flame is like this, horizontal flame, if the flame is vertical, then the flue gas will have a longer residence time. But if the flame is in the horizontal direction, then we're going to have a shorter time, right? A shorter residence time. So in this way, we're basically doing everything we can to control the NOx formation. And so that's why the overfire air is very effective in controlling the NOx formation. And this is an in-combustion technique, right? So last class, we mentioned that we can also do the control techniques with the flue gas. So basically, this is post-combustion. So if we still have some NOx being formed in the combustion chamber, let's say the coal boiler, then we can use this post-combustion technique or flue gas treatment method to take the NOx out, right? So we mentioned that we have the method that's called the selective catalytic reduction. We generally use, let's say, titanium dioxide or vanadium oxide, right? And so on, as the catalyst to get the reaction go through. So in terms of the reaction, that's going to be 4NO plus 4 ammonia and oxygen. So you're going to form 4 nitrogen and 6 water and 2 NO2. Okay. So basically with this method, we're combining the NOx and ammonia to form nitrogen here. So we get rid of the problem of the NOx here. So this is what happens in the flue gas treatment. Okay. So the temperature for this reaction is generally around 300 to 400 Celsius. So this is the optimized window. And we mentioned that if the temperature is too high, so if the temperature is too high, then these extra ammonia will get oxidized into NOx. If the temperature is too low, then basically the reaction is not complete. Then we will have ammonia remained. Okay. And we mentioned that ammonia is a toxic gas. So we cannot let this happen. So that's why we have to precisely control this temperature here. Right. So I think this is where we got in our last class. And there's also a method called selective non-catalytic reduction. Okay, so basically this reaction here, this method here, is not going to use the catalyst. It's just going to use the the temp or the reaction between the gas phases. So what happens is we're also going to introduce ammonia into the reaction, and basically we're using the same chemical reactions to reduce the NOx formation. But the thing is that since we don't have the catalyst, so since we don't have, or there's no catalyst, so the temperature of these two reactions have to be in the window of 900 to 1000 Celsius. Okay, so if you think back on the chemistry or fundamental chemistry you learned, so the function of the catalyst is not to change the reaction. Right? It's not to change the reaction form, reaction pathways. The function of the catalyst is to change the temperature window. And this is what these catalysts are doing. So if you have the catalyst, then you can conduct this measurement, conduct this reaction at 300 to 400 Celsius. But if there's no catalyst, then the temperature window is 900 to 1000 Celsius. But we're still using the same reaction here. And then you may wonder, why does it matter, right? Why does the temperature matter so much? Why can't we just use this non-catalytic reduction here? So the major reason is in this, okay? So let's say we're talking about the flue gas going through different ducts and then along all the way to the control devices, okay? So this is our flame, right? And then we're burning coal in here, and then the flue gas goes this way. These are the water pipes. So let's say if we draw out or plot out the temperature of the flue gas as a function of the distance it travels in the duct, then what we're going to get is, let's say x is the distance from, let's say, from the combustion chamber, let's say just here, just the exit of the combustion location, okay? And y axis is the temperature. So then we can plot out the temperature as a function of distance, and that's going to decrease exponentially. Right? Okay, so I think we can just make it look a little bit better. Okay, right? It's going to look like this. So the temperature will drop down really fast at the beginning because of heat exchange, and then the temperature is going to get flattened out. And finally, if you check the temperature of the flue gas coming out of the stack, that's normally above 100 Celsius, right? So that's why from the stack, really tall stacks here, you can see those white plumes coming out. A white plume is actually just water getting condensed at the after the exit from the stack. So let's say if we draw out the temperature window of 900 to 1000 Celsius and 300 to 400. So they're going to have the same distance on the y axis, right? Let's say this is 900 to 1000. And this is 300 to 400. Okay. And if we draw that out, you can see this. And then after we draw this temperature window out, let's also label the distance that it corresponds to. Okay, so what this means is that for this 300 to 400 Celsius window, that corresponds to a much longer distance compared to the 900 to 1000 Celsius, right? If we label them out, maybe this is the region where it's 900 to 1000. Well, this is the region where it's corresponding to 300 to 400 Celsius, right? So you have to get a very precise control of the location where you inject the ammonia, right? So let's say if you inject it a little bit earlier than this optimized window, then we mentioned that the temperature is too high, we get NOx, right? If you inject it after this, a little bit after this optimized temperature window, then you have ammonia remained, right? And then if we're talking about this lower temperature window here, then we have a much larger range where we can adjust the distance. And also because the flue gas are going to stay for longer under this 300 to 400 Celsius window, then the reaction will be more complete, right? So that's why we still prefer this selective catalytic reduction process, because that gives us more room for the basically for the uncertainty in terms of the location of the ammonia being introduced into the flue gas, right? So basically, for the SNR, that's going to be more difficult to control. Okay, so this is a major difference between the SCR and SNR. And we can also use the adsorption method, which is introducing activated carbon. So the function for the activated carbon is basically the activated carbon are going to have a very large surface area. Okay, so activated carbon can be very small particles, let's say a few microns, but they have a very large internal area, or the surface area. In terms of the activated carbon particles. So because of the large surface area, these NOx molecules can get adsorbed to the surface of the activated carbon. So in this way, we can also remove some NOx in there. But the active carbon actually costs too much. Maybe for some heavily polluted plants. So for some heavily polluted plants, then we may need to use these active carbon to get a higher conversion or higher capture in terms of the NOx. So finally, we have this wet absorption. So wet absorption just means we introduce water into the flue gas, right? So, but in terms of the reaction with the water, there can be nitrogen dioxide react with water, and also nitrogen monoxide react with water. And generally, this reaction is much faster compared to this nitrogen monoxide pathway. So that's why it means that if we use the wet absorption, we want to wait until the temperature gets cooler, right? So if you have a lower temperature, then most of these nitrogen monoxide are converted into nitrogen dioxide, and then we can have a better reaction control here. Okay, so these are the techniques we can use for the flue gas treatment techniques, right? So as a short overview of this section here, so if we compare the capture method between the sulfur dioxide and nitrogen oxides. So let's say if we draw out this table again. So to control these gas pollutants, we mentioned that we have three different ways, three different mechanisms. We have the pre-combustion. Or also for sulfur, that's called basically fuel desulfurization. Right? You remember the reaction between sulfur dioxide and hydrogen sulfide. So we're forming sulfur solid out of it and use that as a raw material for fireworks, right? So that's the pre-combustion method. So we can also have the in-combustion method. And we can do the post-combustion method. okay? So for the sulfur dioxide, we can have the pre-combustion method, that's the fuel desulfurization. We can also have the post-combustion method, which is the wet scrubbing, right? Or the, let's say, trona injection or lime injection. But for the NOx control, we don't have this pre-combustion method, right? It's going to be very difficult to extract the nitrogen out of it. And we mentioned that most of these nitrogen are coming out of the cars or out of the coal combustion, right? So, but we can indeed do this in combustion method by controlling the temperature, controlling the residence time, controlling the oxygen content using the overfire air, right? But also we can use this post-combustion method, which is basically using this SCR or SNR absorption or wet absorption. So after these NOx are being formed from combustion. Okay, so this is the method we can use in terms of the NOx control. So in this class, we're going to talk a little bit about the carbon dioxide, and you can realize that although currently the coal-fired power plants are not enforcing the carbon capture, people are thinking of ways, techniques to capture the carbon dioxide out of fossil fuel combustion. And there are already techniques being brought up on all three pathways. So this is in terms of the carbon dioxide control, although right now it's not being realized yet, okay? So the reason why we're interested in carbon dioxide is because of the global climate change, right? Originally, people say that this is global warming, but we realize that it's not, although the average temperature is warming up, but in terms of different locations, temperature is not necessarily going to warm up. So for some locations, the temperature might drop down. Some locations might get much warmer. Okay, so for example, in Minneapolis, there was a very early snow in end of October, 15 inches. Right? So compared to earlier years, this is a very early snow and it's also pretty cold. Okay, so we would say that this is a category of the climate change because it's very different from before. But it's not necessarily leading to the warming of all areas, okay? So here I'm showing a table of the gas contents that may lead to different global warming effect, okay? So we're still talking about the warming as a global scale, okay? So you can see that the carbon dioxide has the highest global warming effect, okay? It also have an effective year of 50 to 200 years. So what this means is that if we inject carbon dioxide, a large amount of carbon dioxide into the atmosphere, then its effect is going to last for 50 to 200 years until it's being either absorbed by the ocean or being taken by the plants, by the green plants through photosynthesis. Okay, so this is basically going to take a very long response time. So there are also species taking shorter time. For example, the methane, right? Methane is around 12 to 17 years. So there's a species of chemicals, the PFCs or the CFCs, mentioned in the first class, chlorofluorocarbon, right? So for these species, not only they're damaging the ozone in the stratosphere, they're also leading to a global climate effect, global warming effect, and they can last for very long. We mentioned that the reason why people ban CFC is because these are very stable, right? Once they get into the stratosphere, they can basically react with the oxygen for infinite amount of time because they're not being damaged. They're just a catalyst, right? So that's why it's going to take a very long time for us to get rid of the effect from these PFCs or CFCs in terms of their global warming effect, okay? But by comparing all of these gas species, you can still see the carbon dioxide is a key factor. And we have a direct control of the carbon dioxide, which is coming out of the fossil fuel combustion. So I'm going to show you this curve here. I think I also showed you in this curve in our first class when we were talking about the air pollution control, like as an overview. So this is the long-term carbon dioxide observation on the Hawaii Island, so the Mauna Loa Observatory. And you can see that starting from 1960s, the concentration of the carbon dioxide kept increasing, right? It already passed, I think in 2015, it passed this 400 ppm line here for the first time in human history, okay? So we don't know what's going to happen because of this change. But what we know is that the carbon dioxide is contributing around 63% of the global warming effect, okay? So I think nowadays, maybe this is data in 2019. So the average carbon dioxide concentration is 411 ppm. This is always always increasing. Okay, so even if we shut down all the power plants or fossil fuel combustion sources, the curve is not going to decrease immediately. So our atmosphere or our ocean system is going to take a pretty long time to digest all of these carbon dioxide, right? So we also mentioned that there are zigzags because of this in this curve. So we mentioned that the zigzags are because of the seasons, right? So when it's during the summertime of the northern hemisphere, because of the larger land area of the northern hemisphere. Okay, so basically there are more photosynthesis happening in the northern hemisphere. So you can see this carbon dioxide concentration decrease. While during the winter, because there are fewer land area in the southern hemisphere, so their contribution to the photosynthesis is lower compared to the northern hemisphere. So the carbon dioxide will increase. Okay, so we're in this seasonal cycle here. Each year we'll have the concentration drop down and increase up. Right? But in general, as an average, you see this carbon dioxide concentration always keep increasing. So here I have a short video about the carbon dioxide on Earth. Okay. Let's see.
2014 is shaping up to be the warmest year
ever recorded for planet Earth.
cycle change the carbon dioxide. Yeah, so you can see compared to earlier, the concentration here is lower. This is because of the yeah, so finally you can see how these recent years of industrial revolution and also these fossil fuel combustion is pumping up these carbon dioxide into the atmosphere, right? So later on, I'll also correlate with, show you some plots, see how does the temperature correlate with the carbon dioxide concentrations. So in this video, it indeed pointed out some interesting things we need to think about. So for example, at here, it's labeling the country that are most vulnerable to climate change, okay? The reason why they're most vulnerable is because these countries, these areas, they never have a large carbon dioxide emission in their history, okay? So they're not, or also they may be close to the ocean, right? Carbon dioxide concentration, if they increase, then the ocean level increase as well. So they might get impacted by that, but also because they have never been in the environment with high carbon dioxide concentrations. So they might be most vulnerable if the concentration increase up. And also, I think, yeah, so if you also check the simulated results, let's say in here at the beginning, you see the general pattern of these gas flow here, okay? So you can see that in the mid-latitude, the carbon dioxide transport is generally in the pattern from the west to the east. So later on in this course, we're going to introduce why there's a pattern from west to east. It's actually because of the general wind pattern on our Earth, right? So we can divide it into different zones, and that will facilitate the transport of these gas pollutants. And in different regions, they actually have different wind patterns. So that is based on the global, let's say, the meteorology of our Earth. Okay. All right, so let's see here. So here we can have a short, let me see, I should probably share my iPad. Okay. So here we're going to use some time to do a short calculation. So let's say this is also a quiz problem. You can spend maybe 5 minutes to calculate the answer, okay? So let's assume that our the mass of our atmosphere, okay, is about this range here, this mass here. So if the concentration of the carbon dioxide in the atmosphere rises by 1.5 ppm next year, okay, let's say for 2021, if we assume that or increase by 1.5 ppm, let's calculate what is mass of the carbon. Remember, carbon that will have been added to the atmosphere. Okay, so this is you can use the ideal gas law or use these mass fractions to do the calculation here. So I will give you 5 minutes. This is a quiz problem. Let's do that. Okay, so you have 5 minutes to calculate the answer. And the answer is not related to this figure down here, okay? So this is not related to that. Okay, 2 more minutes. So half a minute left. Okay, we'll stop here. All right, so the correct answer is the first one. is 3.17 billion tons. Okay, so I think this question probably doesn't need the ideal gas law for the conversion. You will just use calculate how many moles are there in the atmosphere, and then calculate the mass of the carbon. So we can do it in this way. So we already know that mass of the atmosphere is 5.1 multiplied by 10 to the 21st grams, right? And then first we can calculate what is the molecular weight of the air, right? We know that the molecular weight of the air is 29 grams per mole because it's a mixture of nitrogen and oxygen, right? So based on this information, we can calculate how many moles are there in the atmosphere in total. So basically that's going to be m total divided by molecular weight, right? So find out that yeah, the value is 1.76 multiplied by 10 to the 20th mole. Okay, so we know that the carbon dioxide concentration rise by 1.5 ppm. So we know that basically the carbon dioxide concentration, or this added moles of the carbon dioxide, is going to be 1.76 multiplied by 10 to the 20th, and then multiplied by 1.5 to the power -6, right? We're talking about ppm. So this is going to be 2.64 multiplied by 10 to the 14th mole, right? And we're talking about carbon here, So since we already know what is the number of the carbon dioxide, we can just multiply this by 12, right? 12 grams per mole. That's for carbon. You can find out that this is actually 1.16. Not really. You can just use a calculator online. Okay. Let's say we have 2.64 multiplied by 10 to the 14th, and then multiplied by 12. That's going to be 3.17 multiplied by 10 to the 15th grams, right? And here we're talking about tons, right? Here we're talking about how many tons are there, right? And then basically we need to first convert grams into kilograms, right? That's going to be 3.17 multiplied by 10 to the 12th kilograms. And that's 3.17 multiplied by 10 to the 9th tons, right? And then to the power of 9th, that's 1 billion, right? Or that's also called gigatons. Okay, 3.17 billion tons, or people also call that as gigatons in terms of the mass. Okay, so that's why we're going to choose the first one here, 3.17 billion tons. Okay, so now you have a general understanding of what scale of carbon we're talking about, right? It's around 3.2 gigatons or billion tons here. So if you track the carbon dioxide concentration, let's say the increase of the carbon dioxide concentration, you can see that in general, the concentration will increase around, let's say that's around 2 ppm per year, right? You see, if it's 5 years, then we increased actually more than 10 ppm. Okay, so maybe around 15, so 2 to 3 ppm, right? So what this means is that here we're talking about 1.5. So what that means is we're probably going to dump in 6.4 to 9.6 gigatons of the carbon dioxide into the atmosphere. So basically, this is the increase of the carbon dioxide in the atmosphere, right? And then what this plot shows is a budget of the carbon dioxide over the past, let's say, past few years, from 2007 to 2016. So this is 9 years. So over this 9 years, you can see what is the budget, what are the sources and sinks of the carbon dioxide. See the fossil fuel combustion, fossil fuel and industry, they dump in 32 gigatons over this 9 years, all right? And then this is the source, right? We can also have the land use change. This is biomass burning, right? So if you think about the South Africa, right? So they use this burning process to regenerate the farmland, right? So this process also generates carbon dioxide. So there are also sinks for the carbon dioxide. So there are land sinks, basically the forest, for example, the Amazon forest, they use photosynthesis to fix the carbon back into the earth, right? So there's also ocean sink. We know that carbon dioxide can be dissolved in water. It's like making soda, right? And because of all of these sources, let's say source 1, source 2, sink 1, let's say sink 1, sink 2. Okay, source. So because of these sources and sinks, if you do the calculation, you can see that the source is much larger compared to the sink. So that's what it caused in terms of the atmospheric growth of the carbon dioxide, okay? So you can see that over this 9 years, it lead to around 17 gigatons of the carbon dioxide in the atmosphere. And what we measure, what we calculated, let's say 1.5 ppm, it's gonna increase, it's gonna correspond to around 3.1 or 3.2 gigatons per year, right? So you get this approximate scale in terms of the carbon dioxide emission in the atmosphere. So we mentioned that the carbon dioxide can get dissolved in the water. It's like making soda. We know that if the carbon dioxide gets dissolved in the water, then the water is going to get more acidic, right? So people actually measured the carbon dioxide or the pH of the ocean water over many years. And you can indeed see that the pH gets lower, which means that the ocean is becoming more acidic. Okay. And I think based on your knowledge in 2601, there's also a buffer system, right? You can think of the ocean water as a buffer. The reason why the pH decrease so slow is because of the buffer here, because of the carbonate ions, right? And then bicarbonate ions, right? So if it's not because of buffer, then the pH will decrease very rapidly. And here, now we're trying to correspond the carbon dioxide emission to the temperature, okay? So we mentioned that there's global warming or global climate change. Originally, people used the term called global warming, but later they realized that the warming is not happening at all of the places. So some of the places, their temperature just dropped. And this is mainly because we're talking about the Earth as a huge system, right? So let's say if the water or if the ice at the polar region get dissolved or get basically converted into water. So, and that's mainly because of the global warming. So we know that if we convert the ice into water, that's going to absorb heat, right? So basically it means that this region here may get a little bit cooler, mainly because we're having a phase change from the ice to the water, right? So maybe the Northern Europe or Canada, their temperature will drop down. Well, at the other regions, or if there are seasonal winds blowing these colder air into the more southern area, then that means the temperature also cooled down. But in terms of the entire Earth, the average temperature let's say the average temperature will increase, okay? So what this is showing is the temperature anomaly. So instead of using the absolute temperature, they just compare their temperature against their recorded, let's say the average temperature over the past tens or hundreds of years, okay? So we're showing this temperature anomaly here. So if the anomaly will bias to the higher range, it means that there is indeed a warming effect, right? You can see that from around 1880 to 2010, the temperature anomaly increased by around 0.8 Celsius, right? So the global warming is indeed happening. It's not showing this warming effect at all the places. But if you do the average temperature, plug the average temperature, you still see this warming effect. Okay. So there are also evidence from the basically from the ice cores. Okay, so when people discovered the Antarctica, so since there are no human living in there, right? So they can extract the ice cores, basically a long column of ice, and then track what is the carbon dioxide concentration in that region. By checking the detailed structure, you can also find out what is the temperature over that over the prehistorical time, right? So here it's actually showing the temperature, both the temperature and the carbon dioxide concentration. Temperature in red, carbon dioxide concentration in blue. You can see that over the past hundreds of thousands of years, these two follow very well, okay? So whenever you have warmer temperatures, you have higher carbon dioxide concentration. And this is a greenhouse gas effect, right? So if we emit carbon dioxide into the atmosphere, it's like very more close over the Earth. So you have this very good correlation between the carbon dioxide and temperature here. If you see where we are here, it's like we injected a huge dose of the carbon dioxide to our Earth, right? And then the temperature maybe is still a little bit slow to follow up here. But if we're talking about if let's say these two correspond very well, then the temperature will go up here, right? So what is the temperature here? Right, so on average, let's say the temperature will increase. This is minus, this might be minus 40, right? Fahrenheit. So we're talking about a temperature increase of around 20 Fahrenheit if we follow this trend here. Okay, so this is a very severe issue that people have to really take care of right now. And here are basically more information about this ice core data. So not only we're plotting out the carbon dioxide, we also have the methane here. So methane is also a warming greenhouse gas, right? So you can see that these temperatures and also the gas concentrations correspond really well in the long history of our Earth. And also when we talk about climate, we're not talking about, let's say, last year or 5 years ago, we're talking about very long range of the time, right? Around basically thousands of years. So we're seeing these high temperature region corresponding to these high concentration of the carbon dioxide and methane here. So this is a very urgent issue, and people are actually doing all types of simulations to find out what might be the consequence, because there isn't a very good remedy to solve this issue. Right? We've already dumped a lot of carbon dioxide into the atmosphere. So I think we can just stop here in this class. Next class, we can talk more about the carbon dioxide control. So I did see in the chat that someone mentioned that class 25, lecture 25 is not online. So now it's online. So feel free to go through the content. Okay, that's it for this class.